So we are going to do some more examples with the Turing machines. All right. Um, we do still have homework due tomorrow. It's about Turing machines. Check it out. Um, more Turing machine examples. More. I wrote with an A. Mayor. Turing machine examples. Most of the Turing machine examples that we've done so far involve procedures based on marking off letters on the tape. For example, the standard example for that kind of strategy is this one, where you mark off, say, a typical string in this language looks like this. And the idea is you mark off this A, and then you move yourself to the right, and then mark off this B, and then move yourself all the way back to the left, and then repeat that procedure, all right? Etc. And eventually you end up with all marked everywhere, and then the Turing machine will detect that if it goes all the way through the whole thing and everything is marked, then it should accept, all right? A to the n followed by B to the n you can do by marking. And we did several simple variations on that. For instance, we did, A to the n, B to the 2n. This involves marking one A, and then you go down to the end and you mark two B's, and then you go back to the beginning and repeat that procedure. All right? Let's try one that's a little bit more complicated, but actually not appreciably so. Let's try A to the n, B to the n, C to the n. This example is actually not much more interesting than A to the n, B to the n. Although we all know, like from a theoretical point of view, this language is actually quite a bit more complicated than just A to the n, B to the n, because A to the n, B to the n is context-free, but A to the n, B to the n, C to the n is not context-free, right? We showed that. And many other things like that are not context-free. But you can still do this on a Turing machine. And the strategy is going to be exactly that same kind of marking thing. So I'm going to just sort of try to explain in words. You mark A, and then you move to the right. Over and over again, you move to the right. Continue. As you're moving to the right, you would have to move through the rest of the A's. Let me just I'll try and write down sort of a typical version of this computation. Begins with a string like that, and then after several steps, it will have marked off the first A, and then goes down and marks off the first B, and then goes down and marks off the first C. All right, so I would say you mark A, and then you move to the right past A's and X's, and then mark a B. And then, from there, you continue moving to the right past, this time, B's and X's. That's because you imagine you just marked off this B, and as I go to the right, looking for the next C, you have to go through some other B's, and you might have to go through some other X's, which are the other C's that already got marked. But eventually, you should find a C. So move to the right past B's and X's, and then mark C. And after you mark off the C, you go to the left, basically past a whole lot of other stuff. It could be X's or B's or A's. That's it. There shouldn't be any more C's to the left. So then I'm going to say, move to the left past X's, B's, and A's. And then when you see a blank, that means you're at the beginning. And then you just repeat this whole process. So I'll put a little sort of arrow like that. Once you get back to the beginning, you go back to the very first step there. All right, and this step, I will say maybe parenthetically, move past X's. In the later, this doesn't happen the first time through, but in the later steps, once you get to the beginning, you have to move through some X's at the beginning before you see the first A. So, all right. But this will look very similar to our machine for A to the n, B to the n. Let's see if we can actually make this happen in terms of the diagram. So I'm going to have, what I see here is basically 4 states. That's 1, 2, 3, and 4. And then there's going to be an accepting state also, which we typically don't give a name to. So state 1 says, in this state we should move past any x's, and that it's going to be a loop like this, x, x, r. That means move to the right. When you see an x, you just leave it like an x and move to the right. I hope everyone remembers these Turing machine diagrams. Okay, and then mark A. That means if you see A, change it to an x and move to the right, and go to the next state, state 2. State 2 says move to the right past any x's and a's, so I'm going to put a looped edge on that one with a's, AAR, and also XXR, right? Moving to the right through any a's and also through any x's. And then when I see a B, I should mark it and go to the next state. So I'm going to do, my states are going to be like this, right? BBR. I like the sort of diamond pattern. I don't know about you.
Shouldn't it be BXR?
BXR, yeah, thank you. BBR would mean just go straight through it. I don't want that. BXR. Mark off the B. Come on now. BXR. Thank you for that. All right. And then in state 3, I hope you're doing this along with me. Move to the right through B's and X's. That's a looped edge with BBR and BXR. BBR, XXR. And in state 3, if we see a C, we mark it. So I go CXR. Actually, I'm going to make it, it doesn't matter, but I'm going to make it CXL just because I know at that point, after you mark off a C, your next big journey is going to the left. So we might as well get a head start on that, right? It doesn't really matter, but mark the C and then start going back to the left. In state 4, it should be going back to the left over and over again. So that's a loop like this. And then it's going to go through any X's, XXL, through any B's, that's BBL, through any A's, that's AAL. When do I stop and go to state 1? What do you think? Yeah, if you see a blank. So if I see a blank, I'm going to say blank, blank R. That means if you get to a blank, keep it as a blank and move one step to the right. I got bad news for one of you. I'm not going to name any names, but one of you always writes when you write the letter B. I noticed all semester was writing it like a capital B. Oh, you outed yourself. Yeah. You're screwed now, buddy. You got, because the blank has to be written as a big B. You have to write the little b like a little b. Sorry, dude. Ruin your font choices. Okay, this is basically it. Now, you have to put an accepting state somewhere. Would anybody like to say where is sort of from one of these, there's going to be an arrow that goes out to the accepting state. You have to decide kind of how do you know when it's done? Any thoughts? You know, when it's done, the string looks like all X's. So you might want to think about in this machine here, as described already. At what point will you realize that you had all X's? Yeah. Yeah, I think it's in state 1. In state 1, you go this, XXR, right? So if you're in state 1 and it really is all X's, it means that you will eventually encounter a blank in state 1. This is the only way that you could ever encounter a blank in state 1, is if it ended up being all X's. And so from there, I'm going to make a special arrow out to an accepting state. And I'll just say BBR, blank, blank R here. It doesn't actually matter what you do with the blank at that point. You could change it to something else if you wanted to. And it doesn't matter which direction you move. That last R there is irrelevant. But you got to put something. All right. So this is a Turing machine for A to the N, B to the N, C to the N. Pretty great, right? I guess. Let me just say, could we do A to the N, B to the N, C to the N, D to the N? The answer is, yeah, you could. Actually, it wouldn't be so hard. You would just insert another state, like right here. which does the same basic thing, only it goes to the right some more and then marks a D and then goes all the way back to the left. So the answer here is yes, of course, it's more or less the same. We're not going to bother writing down the machine, but you could if you like. Can I just say anything like this can be done with a Turing machine? All right. So in the old days, or not in the old days, but every so often I've been writing sort of like a diagram of a hierarchy of increasingly complex languages. You know, we had like A to the N, this is regular, and then we had something like A to the N, B to the N. This is not regular, but it's context-free. This is regular. This is context-free. And then we have something like A to the N, B to the N, C to the N. This is non-context free, but you can still do it on a Turing machine. What if you go A to the N, B to the N, C to the N, D to the N? That actually is not any more special than the just three of them. Strange but true fact. Anything kind of like this with matching ends will be, well, if it's big enough, it's not context free, but you can do them all on a Turing machine, right? Anything like that can be done with a Turing machine. I'd say, like, in theory, it can be done, although you might have to change some things around a bit to, you got to be a little, it's not always so obvious as I'm suggesting. Something, for instance, like A to the N, B to the N, A to the N. You might be tempted to say, well, this is more or less exactly the same as that, except the C on the end, it's just A's instead of C's, right? And so maybe I could just use exactly the same diagram, only right here where it's a C, maybe I'll just make that an A. This actually, I think, is not so easy, because the fact that there's A's at the beginning and also A's at the end means that, for example, this part refers to these A's. You got to make sure these are only the A's at the beginning and not the A's at the end. You don't want to allow the A's at the end to influence the behavior right here. So actually, it's not so simple as I'm suggesting. I'm not saying it's impossible. Actually, I'm sure that it is possible on a Turing machine. It's just not so obvious, or not so simple to just change the diagram simply. I think if I had to do something like this on a Turing machine, maybe I would make a machine, first of all, which just walks to the end of this and changes all these A's to C's, and then run it through that other Turing machine, right? That's a simple way to use the machine that we did first. Just make all of these A's into different, that's easy to do. You could run all the way to the end of the string, and then go backwards, and every A you see every A change to a C until you hit a B. That means you're done with the A's at the end, and then you can go back to the beginning and run through the other machine. Anyway, I'm just saying, all of these kinds of things can be done with a Turing machine, although it's not always boneheaded simple, right? Let's try. I got two more specific examples, and then I have one for you guys to try, which I hope we have enough time for. These can be kind of complicated. Let's try, how about this? A to the N, B to the M, C to the N plus M. All right? The idea is simple enough, I think, although there's some kind of tricky, slightly confusing details to it. But anyway, for example, a string in this language would be something like A, B, B, C, C, C. And my concept in marking things off would be, let's start by marking the A. Here, I'll write it in very vague words, first of all. I would mark A, then mark a matching C, right? Actually, I'm gonna say this a little bit differently. Sorry. I'm just gonna say mark. There are a few ways you could try and do this, and each would be possible. I'm just gonna say mark each A with matching C. So if I were doing this step by step, I would first mark the first A and then mark the first C, right? And I would continue to do that until all the A's are marked. Now, in this example, all the A's are marked immediately. And then I would go through, mark each B, and match it with a C. And then hopefully at the end of that, everything will have been marked. So I'm going to mark each A with a matching C, and then mark each B with a matching C. And then, provided that everything is marked at the end, it should be accepted. All right? This is how I'm going to do it. It's a little tricky. So my strategy for this is really this right here. This whole thing right here is something like, it's very much like the Turing machine for if it was just like A to the N, C to the N, right? I'm marking all the A's and also marking the same number of C's. And then after doing all that, I send it through this part, which is like, again, this is like the Turing machine for, well, I'll call it B to the M, C to the M, right? After having marked all the A's with their matching C's, I then go through the whole thing again, marking the B's with their matching C's. All right, this is the idea. Now, this Turing machine for A to the N, C to the N, sorry, I keep scrolling to the right. It's basically going to have 3 states here going. It's the last time I'm going to scroll to the right. It has 3 states going like this. The first state, you mark the A, and then you move to the right over and over again. Then you mark the C, and you move back to the left over and over again. So this was like 3 states. If you look back at your notes from last time, you see a machine like this. And then this one also has another 3 states to do the B's and the C's, right? You mark a B, and then you go to the right until you find the C. So really what it's going to look like, my diagram is going to look sort of like one of these, and then it has an arrow coming over to this one, and then it goes through this one, and this one has an arrow going to an accepting state. This is the very vague model for how this is going to look. All right, it'll look complicated if you just try and write the whole thing out of nowhere, but this is my idea. Okay, let's see if we can do it. So I'm going to maybe, just so that I don't have to scroll vertically, because I know folks don't like when I scroll vertically, I'll try and arrange them like this. State 1, 2, 3, where this is the one where it marks the A and the matching C. All right. So we begin in state 1, as always. And state 1, first of all, just like before, you may, in the later steps, have to move through some X's. Those are A's which have already been marked. I'm looking at, I'll just make up another example here. If I have 2 A's and 2 B's, then I should end up with a total of 5 C's. And in this step, I'm doing things like this. So I mark the first A, and then I have to move through a bunch of junk, which is A's and B's and X's, in order to find the next C. So I go over here and mark the A. So this says A, X, R. And then in state 2, I move to the right. This will go through some A's, also through some B's, and also through some X's maybe. Those are some C's which have already been marked. And then I find a C and mark it. So I go C, X, R. Actually L here, because once you mark the C, you should start going back to the left. And then state 3 is going to go to the left through everything. It should go through X's and B's and A's. And then when you see a blank, you're back to state 1, BBR. All right? Okay, so this is the basic sort of first step, which is to mark all the A's and mark off the corresponding C's for those. All right? Now we have to ask ourselves, what is the signal in this machine that you are done with the first step? That is, you've already marked off all the A's. Anybody say when in this, you know that? Yeah. Yeah. Okay, so if you go left, the going left is in this step. So it's kind of an unfortunate way that we wrote this machine. When you're going left, actually, there's no signal that you don't see any A's. Like you might see a bunch of B's and X's. You might also see A's. You get to a blank. Let's just imagine what would happen if there were really no A's. You would go through, I mean, there wouldn't be any, but you wouldn't notice. Then you get to a blank. You go to state 1. Now you move to the right. You see a bunch of X's. You go through all of those. Actually, I think if you're in state 1 and you hit a small B, that means you must have marked off all the A's already, right? You move through a bunch of X's, and if you get to a little b from here, then you have marked all the A's. So I'm going to say, if I hit a little b in that step, and here's a little non-obvious thing, but what should you do if you see a little b in that step? I think actually you should mark it, right? Because this is like the first step of your next loop. So I'm going to say B, X, R. That means actually in my next part of this machine, which is going to look again like one of these, actually this is a cute little variation. It should go up there, right? Because I will have already marked the first B. Rather than starting in what would be analogous to state 1. I should start up here because this is the, like remember in our original setup, this is where you go after you mark the first A. You go to state 2, right? And as I'm jumping over to the second part of the computation, actually you should jump in at this point because I've already marked the first B. But anyway, other than that, this diagram should look similar to the one I just did. So in this state, maybe I'll just start down with state 1. I'm not going to call it state 1 anymore, but it is similar. So this is the one in which you should move to the right through any X's and then mark a little b when you see it. Okay, and then up here we need to move to the right through any remaining little b's and also through some X's, which are C's, which are already marked. I'm going to go BBR, CCR. All right. Now the first part of this machine also said AAR, but I actually don't want that here because you're not supposed to see any more A's, and if you did see another A, you should not accept the string. It should jam the machine and reject immediately. So I'm not putting A's. I don't know if it's even possible to have A's there. All right, next you're going to move all the way to the right, so you see a. Sorry, there should not be a CCR because I meant to say XXR there. We are moving to the right, looking for a C, XXR. Moving to the right, looking for a C, which is supposed to get marked. So once you find a C, you mark it, CXL, I'm going to put, and then you go back to the left. This is very similar to the other part of the diagram here. XXL, BBL. I'm not going to put AAL because the A's should all be gone by now. And if you do see an A, it should jam. You want the machine to reject. All right, and then, as before, I'll say blank, blank, R. All right. So this part of the machine is all good, and now we finished like before. So now, if you actually do get all the way to the end and everything was X's, you will notice that, come on now, you will notice that in this step, you move all the way to the right and see only X's. So if in this state you see a blank, that means you're done. So finally, blank, blank, R, accepting. All right. This is how we do it. This is kind of a complicated example, but I would like for us to think about being able to kind of plug one machine after another one or something like that. We're doing one type of computation and then followed by more or less the same thing again, although it's not exactly the same thing, of course. All right. Anybody got any thoughts about that? You can come up with some pretty absurd or crazy-looking diagrams, which you can impress your friends with if they're looking over your shoulder. All right, great. like I said, I got one more example and then one for you all to try, although now looking at the clock, we may not get to the you try part. Maybe we'll just start off next time with it. Okay, one more example. Let's try this. This one is quite different, I guess. But still, we're going to do this by some kind of marking procedure. Although this has an extra little subtlety to it. Something slightly different is going to happen here. So, x, c, x, where x can be anything, any string of a's and b's. So it's strings in here look something like a, b, a, c, a, b, a, or b, a, b, c, b, a, b, right? You've got just the same thing. You've got one thing, and then a c, and then the same thing again, right? That's how this works. Or B, A, C, B, A, right? A thing, a C, and then the same thing again. This is not context-free. Actually, even just the language XX is not context-free. XC, X also is not a context-free language. But you can do this using a Turing machine, and I'm going to do this by marking. There's a bit of a, well, it doesn't seem any different, actually. If I, say, started with A, B, C, A, B, how would you do this by marking? I would say you begin by marking the first A, and then you move to the right, and my goal is to mark off the matching A on the right side. Now, you might be worried about, maybe I'll do a, sorry, I'll draw a more complicated example, just so we can, how about this? So you begin by marking off the first A, right? And then I have to move to the right to find the A that I'm supposed to match it with. Now, you might be worried about, well, aren't I going to get fooled by this A? The answer is, you kind of use the C here as a trigger to tell you when you've looked far enough. So I am going to start by marking this A off, and then I just move to the right through whatever until I see the C. And then after the C, the first A after the C is the one I match it with. So this is going to match with that A, right? And then in the next step, I just go back to the beginning and starting from this B now. I mark this B. I move to the right through a bunch of stuff that I don't care about. Once I see the C, then I'm going to start looking for the B to match it with. And then I match it with this B here. All right, etc. The very end is just going to have the C surrounded by a bunch of X's. And that's how you know that it worked, is that you end up with just the C in the middle. We'll have to talk about exactly how you see that, but this is the basic idea, all right? Okay, let's see if I can write down some steps here. So what I would like to say is something like, let's start by mark the first letter. It might be an A, it might be a B, whatever it is. Mark it off. And then you start to move to the right. Move to the right through, what am I going to move through? I guess just A's and B's, right? And then something special will happen when I see a C. So I'm going to say move to the right through A's and B's. And then when you see a C, you want to actually kind of continue to move to the right after the C, but you're in like a different state at that point. So what I'm going to do is move to the right through A's and B's, and then when we see the C, you just sort of, again, move to the right, but go to a new state now. And then I'm going to say move to the right through X's. After you pass the C, now you're only going to move through X's until the next letter you see that's not an X. If it's the same as what you marked at the beginning, you mark that one. So I'm going to say move to the right through X's. And then if we see the first letter again, whatever that letter that we started on, it might have been an A or a B. If we see the first letter, mark it. And then move all the way to the left. and then repeat this whole procedure, right? So how many states do we have here? I would say this is like one state here. This is another state. I'll call this state 2. And then this is state 3, and this will be state 4. Right? Those are the 4 different types of behavior. And then we go back to state 1. Now, I said before, there's a subtlety. I don't know if you've noticed this, but there's one step here which is not really obvious how we're going to do that. And this right here, if we see the first letter, you have to somehow, when you get to, say in this example, I mark this A, and then I go to the right, past the C, and the next thing I see is an A here. Now, if it really was an A, you should mark it and continue, right? But what if it was a B? Actually, if it was a B, you want the machine to stop and reject the string. But on your diagram, how do you make it? Like the arrows on the diagram, they can only either say like AXR or BXR. They can't say something like, this one over here is the same as that one over there, right? There's no such thing on a Turing machine diagram. And so the trick to make this happen is by 2 branching paths. And it will become clear immediately when we do the example how that is supposed to look. But in order to make this kind of, if this thing was the same as that thing over there, you have to do this in what I'll call 2 branching paths. All right? So actually, what we're going to do is, state 1 is the same either way, but when it goes into state 2 and state 3, I'm going to make actually like 2 parallel universes. State 2A is state 2 in the scenario where the first letter you saw was an A, right? And then state 3 also has these kind of like 2 parallel universes. Once I get to state 3, there's the one version in which the first thing I saw was an A, and then another version in which the first thing I saw was a B. And this allows you to handle the 2 different scenarios about which one you saw. And then by the time we move all the way to the left, actually it doesn't matter anymore which one we had seen at the beginning. So state 4 does not need to be split into 2 separate parallel tracks. So how I'm going to draw this is I'm just going to try to draw the basic structure. I'm going to put 1 here, and then I'm going to make it look like 2A to 3A, and then to 4. So I'm going to make sort of 1 path like that, and then 4 goes back to 1. And then I'm also going to make 1 goes to 2B, to 3B, to 4, and 4 goes back to 1. This is the general sort of shape of the machine that I'm about to draw in more detail. All right, let's see if we can do it. So, sorry I have to scroll past my instructions here. State 1 is my starting state. Now, I didn't write this in the steps, but you have to put this in there, XXR. This will, at the beginning, in the later steps, you have to push yourself past a bunch of already marked letters. So I'm going to move past some already marked things. And now, either the first letter that I see is an A or it's a B, and that will immediately send me into these 2 parallel tracks. So if it's an A, I mark it, AXR, and I'll go into state, what I call state 2B. Not B, A. 2A. This is state 2 in the version where, in the scenario where the first letter that I saw was an A. And then I'm also going to, if the first letter is a B, these are like 2, this is what I meant by 2 parallel branching paths. They're going to do the same things, more or less, either path. They just have to be separated out of 2 different versions. If your alphabet had 3 letters in it, unfortunately you would have to make 3 separate paths, right? Depending on the first thing you saw was an A or B or C. Okay, let's just fill in the top path first. So if it's a 2A, I want to move to the right through any A's and B's. How would I indicate that on the diagram? I see someone making the signal with their hand like this. You want some loopies that go from here back to here, just moving through any A's, so that's AAR and BBR. Right? When you see the C, actually you don't really do anything to it. You need to leave it like a C. But now I move into state which I will call 3A. This means I'm now past the C. And you think, what should I do then? Well, you might have to move through some X's, which are some already marked things. That's like this, XXR. But then if I see the letter that I saw at the beginning, which in this branch was A, then I should mark it and start to move to the left again. So I'm going to say AXL. And then into state 4. State 4 just moves to the left over and over again, no matter what you see. So this will go AAL, BBL, CCL. It will go through the C eventually. It will go through a lot of X's. Eventually it sees a blank. When you see a blank, you go back to the original state, like that. All right? So this is the A track. You saw A at the beginning. This will go over to the right, past the C, and then mark off the next A. Okay, and then if you saw B at the beginning, you do basically the same stuff. 2B is still going to go past any A's. I might as well make it look just like that. BBR, AAR, CCR, over the C, and then after the C, you only want to see X's. XXR, and going up to state 4 by doing BXL. So this will mark another B on the right of the C. All right. This is the basic machine here. We just need to add in information about ending the computation. The accepting state, you have to think about what will happen. And I'm tempted to look at state 1, right? I think of this whole computation as some kind of cyclical thing. You do this big procedure until you get back to state 1. And you keep on doing that over and over again. The check to see when you're done, to me, it's most natural to check when you're done right here, right? Any thoughts? What should happen in this state if you're actually done? Yeah. So yeah, when you're done is when you see C from this state, right? I hope that's clear. When you're done, it means you've marked off everything to the left of the C, and you get to a C. So I'm going to say here, C. Now, if you like to, you could change the C to an X on the tape, but actually it doesn't really matter what you do with the C. I mean, you're gonna accept, right? So do whatever you want with the C. I'm just going to say CCR. Now, you may be tempted. I just said it, actually. This is not right, what I just did there. I put an accepting state there. Not right. Actually, can anybody think of why? If you see a C there, that does not necessarily mean that the string should be accepted. Yeah. There may be extra stuff on the right. For instance, if my string to begin with was this, then the procedure we've described so far will actually correctly mark off all of these, and then it will go back to the beginning. But of course, it will go back to the beginning and then march up to the C. It says, I saw the C. You should not accept this string though, because it had a bunch of extra junk at the end. So, you want to suggest how we fix that? Or how we have to continue. This is not the accepting state. We have to continue and do a little bit more stuff to continue to verify that there's no extra junk at the end. Yeah, keep going to the right through X's until you see a blank. If you can really do that, then you really are done and everything is acceptable. So, I'm going to put like this, XXR. This will continue to go the right, only moving through X's. And if finally you see a blank at the end on the right side, then you really are done. This is something that can be quite tricky to like make sure you really got to the accepting state at the proper point. It's not obvious, and unfortunately when you're doing these Turing machines, it's not completely obvious that this is still correct. Like, is there any other kind of even more insane example that maybe would violate this machine? The answer is I don't think so. I mean, I think that this is correct, but it's not. You may feel unsure of yourself, and that's okay. This is a safe space. Although I will mark it wrong. Yeah. Yeah, so what will happen in this machine? This is a good question. What does happen if there were extra A's there? Well, it would, so I get to this C, and then I go down to that next state, which would move to the right through all these X's, and then I would end up with an A here. So in this diagram, I would end up on this state, and I would see an A. Now there is no arrow here for what to do when you read A. That means the machine stops and the string is rejected, which is exactly what you want in that case, because that string should not have been accepted. All right? Great. We got 6 minutes.
Did you ever learn how to change it from the DFA to the machine?
I did not.
There's that question.
That's on the homework. Yeah, and that's kind of the whole question. So I don't want to tell you how to do it. But I gave you a hint, right? I guess it was not helpful. You didn't think there was a hint? Oh, there should have been a hint. The hint was you should make your machine so that it always moves to the right and it never changes what's on the tape. Does that sound familiar? Did I not say that? That was supposed to. Did anybody else look at the homework? I appreciate you looking at the homework before the day's due, by the way.
I think it was there.
Did I say that? Yeah. Yeah, so you want your machine to basically, if you already have a DFA, if the string is something like this, I don't know, make it so that the Turing machine, it starts by pointing at this letter. You should just make it move to the right every time and change its state every time, based on what the DFA looks like. I don't know if this is helpful for me to say this right now, but yeah, I think that my hint was pretty insightful, although apparently you disagree. See, think about it a little more. I can try to explain some more tomorrow if you're still thinking about it. Yeah. I was going to say there's not enough time to do the other example, so maybe we'll just start off next time with another example. It also involves this kind of branching paths thing. All right, I think that'll do it then. See you all tomorrow.
So for that homework question, do you want to make the DFA first time so it's
Yes. I mean, the idea is if I give you a DFA, you turn the DFA into a Turing machine.
Okay.
And the answer is like you basically draw the same states and the same arrows, but you have to
make sure it goes to the right every time.
yeah, make it move to the right every time, make it not change the tape in any step. You have to say a little bit about how you handle the accepting state. All right. Yeah. All right, see ya. Goodbye, folks at home.